This demonstration looks at a model of the initial phase of a liquid quenching process called film boiling, which happens when a vapor layer separates a hot solid from a cool liquid. In the graphics window, we see a cutaway view of the model. The outer cylinder represents an oil quenching bath, and the inner cylinder, or puck, is a piece of solid metal that is placed into this bath at a very high temperature and rapidly cooled. A surface plot of the volume fraction of vapor is shown in the oil bath domain, while a surface plot of the temperature is shown on the puck. White is the hottest, and black is the coldest. Let's animate these results in time. This video shows about 40 seconds of the cooling process, during which gas bubbles are quickly formed along the walls of the puck and then float up and out of the top surface. During the 40 seconds, the temperature in the outer areas of the puck here drops from over 1050 degrees C to under 950 degrees C, while the interior of the puck is still relatively hot. Quenching into liquid media is an extremely complex process involving a variety of physics operating on vastly different scales. The near-wall boiling processes that strongly influence heat transfer from the part to the quenching medium operate on a scale that is many orders of magnitude smaller than the component size. To accommodate these different scales, the complex 3D physics near the wall are modeled using equations that are solved only on the walls of the component. Here in the model builder tree, under this physics interface here, we see the boundary equations that are defined along the boundaries here, this 2D axisymmetric geometry. This is a multiphysics analysis solving for multiple variables, including the temperature field histories of the puck and liquid, as well as fluid flow variables for a two-phase turbulent bubbly flow. In addition, the boiling layer, which I just described here, is modeled using a custom proprietary set of boundary equations. The boiling layer thickness, which of course in real life has a finite thickness, will not be explicitly modeled. Instead, the boundary PDEs approximate the mass, momentum, and energy transfer in the boiling layer. COMSOL's custom PDE interfaces available with the base package easily allow for these equations to be coupled with the conjugate heat transfer physics. Let's take a few minutes and go through an overview of how this model was set up. First, the geometry. The geometry is pretty simple. It's a 2D axisymmetric geometry. This is the axisymmetric axis here. We see the puck here in the middle in a cylindrical bath of the quenching liquid. The corners are filleted here and here to avoid undefined derivatives in the boiling layer equations. As far as the material definitions go, that's defined under the materials node here. The metal puck is made of a nickel superalloy called Inconel 718, which is available in the COMSOL material library, and it contains heat transfer material properties that are temperature dependent, as shown here. The liquid is a quenching oil, a generic quenching oil. The equations to be solved are specified under 4 physics interface nodes shown here in the model builder tree. 2 separate physics interfaces are used to solve for their own temperature variables T and T2 in the 2 domains. Here, this first interface solves for the temperature T in the puck. The second interface defines equations in the oil domain and solves for this temperature T2. This is an easy way to allow the temperature at the boundary between these 2 connected domains to be discontinuous. Remember, we aren't explicitly modeling a domain for the boiling layer. Rather, we are solving a set of PDEs directly on the boundary. The heat flux boundary conditions out from the puck and into the liquid are used to couple the 2 sets of heat transfer equations at this interface. Let's talk about the heat transfer equations in the puck domain, which are defined here. The default axial symmetry condition is accepted along the symmetry axis. Under heat flux 1, a general inward heat flux is applied using a variable called heat flux puck. A negative sign here is added because heat is flowing out of the puck and into the liquid. This variable is defined under definitions variables 1. It's shown here. The exact expression is grayed out due to its proprietary nature, but I would like to say that this variable is a function of solution variables described and solved for by the custom boiling layer PD interface here. You see these variables BL1 and BL2? The variable, again, up here under definitions variables, heat flux puck is a function of those solution variables. So these are how the equations are coupled. Back to the heat transfer interface. You see here that there's also a surface to ambient radiation condition applied. And this will contribute along with the heat flux that I just described. This fully defines all the essential and natural conditions needed to arrive at a meaningful solution of the temperature field in the puck. A similar setup is used to solve for the temperature field within the oil bath domain. We won't cover the details in this demonstration. Let's move on to the turbulent bubbly flow interface. Here. Let me contract some of these. The first thing I'd like to point out is this gravity domain condition. This is applied to the fluid to allow for buoyancy effects. The wall 2 boundary condition here, applied to the top of the fluid domain, allows for the liquid phase to flow tangential to the boundary, but not normal to it, while at the same time allowing the gas to flow freely out of the domain. These conditions are set up here. One really nice feature in COMSOL is that if you ever have any doubt about what boundary conditions you are applying, you can always view the mathematical equations in the settings window under the equation section here. Whenever the Navier-Stokes fluid flow equations are solved, it's required for uniqueness that the pressure be specified somewhere in the domain. That's why we have this pressure point constraint. As you can see here, it's defined in this upper right corner of the oil domain. And it specifies a 0 pascals pressure at the upper right corner. Probably the most interesting boundary condition in this interface is this wall 3 condition. It's applied to the boundary where the liquid touches the puck. Notice a gas mass flux is applied here using this variable gas flux. Similar to the custom heat flux is applied earlier, this variable is also defined under definitions variables 1 and is a function of the boiling layers variables solved for by the custom PDE boiling layer interface, defined here. So that's a brief overview of the physics setup. Let's move on to meshing. Under mesh 1, we can see that a custom mesh has been set up. A custom meshing sequence has been set up. That includes a boundary layer mesh in the fluid domain at the boundaries where the puck touches the fluid. This is an efficient way of resolving the strong gradients in the solution variables in this area. Now that I've shown the setup for our geometry, physics, and mesh, the next step would be to solve. Solving in COMSOL is done using this study node. As you can see, the time-dependent form of the equations is what we're solving. And we're going to be solving for a period of about 40 seconds, running from an initial time of 43 up to 83. All variables are solved for simultaneously using a segregated solution approach. I already have the solution stored, so I won't need to resolve here. But in order to compute the solution, if you're going to do that, you just right-click on Study 1 and select Compute. The time-dependent solver completes in about 30 minutes, on my machine, which is an average current market workstation. We already saw an animation of some of the solution variables on a section view of a revolved 3D geometry. But let's take a closer look at what's happening during this quenching. Under results, I'm going to click on this 2D plot, volume fraction of vapor, resize my graphics window. So this is the 2D axisymmetric plot. And as you can see, that we're plotting the volume fraction of the gas phase coming off of the puck. And you can see an area where the gas phase is highest here. We're plotting this at an instance of 2 seconds into the simulation. And notice that right away the boiling layer begins releasing a gaseous phase of the oil into the surrounding liquid with the highest concentration along this outside vertical surface of the puck. The bubbles quickly float to the surface due to the buoyancy effect. I have another plot set up here called thickness of film. And in the graphics window you can see here's a vertical slice plot through the center of the cylindrical geometry. And I've mirrored across the 2D axisymmetric plane. So this is the full diameter of the puck here, and this is the full diameter of the bath, and sliced right through the center. And what I'm showing here is this tube plot with a height expression defined, which gives a visualization of the thickness of the boiling film layer. Areas in dark red correspond to a thickness of about 6 millimeters, and areas in dark blue correspond to a thickness of less than 1 millimeter. As expected, at the bottom of the puck, the vapor is trapped underneath due to upward buoyancy force. So that's why we have a high thickness of the boiling layer here. The spikes here at the edges and in the middle of the top of the puck correspond to areas where relatively large amounts of gaseous bubbles are being introduced into the liquid. Again, I'll show the initial plot that we showed of the puck after 40 seconds in the cooling bath. You can see again how the outer skin of the puck after about 40 seconds of cooling in the oil has cooled relative to the center of the puck.